Hello, everybody. It's Dr. Rehse coming to you again with another great DoD STEM Saturday. This is our December session. So we are celebrating our MANIDOO-GIIZISOONS, which is the little spirit moon in Ojibwe, DICIEMBRE in Spanish, December English session of our virtual Great Lakes Region and Tribal Nations Open STEM topic Zoom learning session. Because it is the December session, we are acknowledging the celebrations of the winter solstice, Hanukkah, Las Posadas, Christmas, and Kwanzaa this month. So welcome everybody, no matter what it is you're celebrating. So because this is our December edition, I'm going to be talking today about winter is coming, a very timely type of idea. It's starting to get cold outside. The trees have all lost their leaves. There's no doubt in any of our minds that winter is in fact coming, so it's time to get ready for it. So we're going to talk about winter today. So let's go ahead and jump right on into it. So we will share my screen. There it is. So as I said, winter is coming. My name is Professor Steve Rehse. I'm a professor of physics at the University of Windsor in Windsor, Ontario, Canada. And if you are thinking that that title, Winter is Coming, sounds familiar, yes, I in fact did blatantly steal that from Game of Thrones, which almost everybody knows. So here's Ned Stark on the screen, and anyone who knows anything about Game of Thrones knows that winter is coming are the house words of House Stark, and they're always getting ready for winter. Well, for us, we do indeed have to get ready for winter coming right outside that window. So that's where that is coming from. I want to start with our land acknowledgement statement before we start. The University of Windsor does sit on the traditional territory of the Three Fires Confederacy, the First Nations, which includes the Ojibwe, the Odawa, and the Potawatomi. We respect the long-standing relationship with First Nations people in this place and the 100-mile Windsor-Essex Peninsula and the Straits or Le Détroit of Detroit. So let's go ahead and just jump right into the idea of winter. Winter is coming. Why is winter coming? That's what we want to talk about today. Well, we need to keep two basic facts about planetary physics in mind to understand why winter is coming. First thing you have to know is that all planets revolve around the sun. So there's this idea of revolution. The revolution of the Earth is the motion of the Earth around the sun in its orbit. All the planets, kind of shown in this cartoon that I have animated on the screen here, are all revolving around the sun roughly in one flat plane. We call that the ecliptic or the ecliptic plane. It's kind of like a saucer that extends out through the solar system. All the planets are revolving roughly in exactly that same plane. Of course, the Earth makes one revolution of the sun every 365 and a quarter days. That's what's going to give rise to the fact that our years are 365 days long. It's set by the revolution of the Earth around the sun as it makes that orbit around the sun, and all the planets do that. Another thing you need to know is that all of the planets rotate about some rotational axis. So there's revolution, which is the motion of the planet around the sun, and then there's this rotation, which is the spinning of a planet about its rotational axis. And I have that animated on the screen here for you as well. Of course, the Earth makes one rotation every 24 hours. That's what gives rise to the days and the nights. So the rotation gives us days and nights. So you can see that you can imagine, obviously a rotational axis is nothing you can see sticking out of the Earth, but there's definitely a northern pole and a southern pole. It's as if there's a pin stuck right through the planet and the Earth is just spinning about that pin. That's what I mean by the rotational axis. So here's the sun. So we are revolving around the sun, and at the same time, we're rotating about our axis. There is one little quirk of the planetary dynamics that is going to give rise to the seasons that we know. And it's this fact right here. It's the fact that the axis about which we are rotating is actually canted or tipped away from being straight up to the sun. And I'm going to show a lot of different animations about this so you can really picture it clearly in your mind. But this is what we mean when we say, and you'll commonly hear this, the Earth's axis is tilted by 23 degrees, 23.5 degrees actually, but a lot of times people say the Earth's axis is tilted by 23 degrees. That's what we mean. So instead of just going around the sun like that, as it spins, it's just tipped a little bit towards it. And so it's going to have some very strange orientations as it makes that revolution. The long and short of it is that sometimes we're going to be pointed in the northern hemisphere towards the sun, and sometimes we're going to be pointed away from the sun. And that's what's going to give rise to our seasons. So let's see how that all plays out in these stellar dynamics. So here's another great animation. So now this is doing far better than what I was trying to do with my fingers. When you combine this revolution, which is the 365-day journey around the sun, combine that with the tilting of the Earth's axis, you get what we call here on Earth seasons. Now, take a look at the northern hemisphere, which is where we are up here, somewhere near the top part of this little axis sticking out of the Earth. You're going to see sometimes, like when we're over here, we are pointed away from the sun. That's going to be winter for us. And then there's going to be times when we're over here on the orbit where we're actually pointed towards the sun. That's going to be summer. So that's going to be winter right here, spring right there, summer when we're over here, fall right here, or autumn, and then winter again. So it's the combination of that tilt and the fact of that motion, which means sometimes you're pointed at the sun, sometimes you're pointed away from the sun. And so really, this is how the seasons come to be. And these dates are very, very important dates because we know exactly the times and days when we are most tilted away from the sun and most tilted towards the sun. So winter is in fact coming because in the northern hemisphere, let's just pay attention to the seasons in the northern hemisphere in yellow here. Winter is going to occur, or it starts on that date when we are tilted the most away from the sun. And that's going to be December 21st or 22nd, and we call that the winter solstice, the shortest day of the year, because in the northern hemisphere anyways, because when we are tilted away from that sun, as the Earth rotates, the sun is going to be very low in the sky, and we just are not getting as much sunlight at all. So December 21st, 22nd, the winter solstice. Conversely, in the summer, somewhere around June 20th, June 21st, we are the most tipped towards the sun, and we call that the summer solstice. Those will be the longest days of the year, the most hours of sunlight in a day. And then we have these other dates of September 22nd and 23rd, which is the autumnal equinox, and March 20th, 21st, called the vernal spring equinox. And these will be the days when the day is exactly split between 12 hours of day, 12 hours of night. So there's the halfway point there. So the equinox occurs when you have equal amount of day and night. Obviously in the northern hemisphere, summer, we have more than 12 hours of sun a day, and in the winter we have less than 12 hours of sun a day. But it's not just going to be the number of hours of sun a day that's going to give rise to the seasons. That might have something to do with it, but that's really not the main reasons why you have the seasons. So we are going to see that the seasons are kind of parameterized by two different things. One, like let's talk about the winter solstice. The days are going to get much, much shorter, but also it's going to be much colder because we're going to be receiving a lot less solar energy. So now you at least can understand what spring, summer, autumn, and winter are. And again, for the northern hemisphere. So for any of you out there watching in the southern hemisphere, first off, welcome. Thank you so much for watching. But of course, their seasons are opposite, because when you have these times over here, say the summer in the north, when we're most pointed towards the sun, when the southern hemisphere, look down here, they're pointed furthest away from the sun. So their seasons are always exactly opposite. Sun in the northern hemisphere, winter in the southern hemisphere. December 22nd is just around the corner. That's going to be winter in the northern hemisphere, but starting of summer in the southern hemisphere, all due to that 23.5 degree tilt of the axis. So why does that tilt of the axis lead to the seasons? Well, look at the amount of solar energy that's following. So these yellow bars right here are kind of simulating a bunch of sunlight. I don't know, imagine like a square meter of sunlight kind of coming through space and falling on the Earth. This will be the summer. When the northern hemisphere is tilted towards the sun, those sun rays are going to strike the Earth at a steeper angle. The sun kind of comes in directly, and all of that solar energy is concentrated on a smaller spot. And so there's more radiation per unit area to be absorbed. Everything is going to be warmer. You're getting literally more solar energy per square meter in the summer months. Conversely, in the winter, just look at these same things, these little patches of yellow indicating this, say, square meter cross section of sunlight. Look when it falls on the north as the Earth is tipped away. That same amount of energy is kind of smooshed out over a much broader area because it's hitting at a glancing angle. It's not hitting the Earth dead on, which will be very effective at heating. The Earth is now tilted away. Those sunbeams kind of come in and they're all spread out. So it's the same amount of energy coming from the sun, but it's spread out over a bigger area. Not as efficient at warming. Less energy per area to be absorbed just means you're going to be colder all the time. All right, and of course at the equinox is when these are approximately equal. So during the equinox, of course, at the equator, you'll be the warmest, but up at the Tropic of Cancer and the Tropic of Capricorn, then you should be getting equal amounts of solar energy. And here's a nicer picture that actually shows that. So forgetting the tilt of the Earth for 1 second, from this explanation, now you can actually understand why our poles, the north and south poles, are always going to be cold. All right, so let's not worry about the tilt for now. Assume that even if we were standing straight up, just look at these rays of light coming in. Again, imagine it's just like a square meter of light coming in. At the equator, you're getting all of that solar energy, bang, right on the surface of the Earth. The Earth is curved away though. So as you get further and further to the north, look at how the same amount of energy. Do you see how it's spread out over a much bigger area? It's the same amount of energy. It's just shared over a bigger surface of the globe. It doesn't heat as well. There's not as much radiant energy arriving per unit area on the surface of the Earth due to the tilt of the Earth, the curvature of the Earth away from that sunlight. So it's the same amount of energy, which is heat, spread out over a much larger area due to the curvature of the planet. So even without a tilt of the axis, the north and south poles of the Earth are always going to be cold. This tilting actually amplifies that effect a lot, or it can counterbalance it. So here's that patch of sunlight again. Now I'm indicating probably the summer solstice, right? Because the sun's over here somewhere. Our axis is tilted towards it. So here's this bit of sunlight. It falls on the sun, and all of that sunlight is going to be absorbed into this area right here, however big that is. So let's just move that off to the side and keep an eye on that for reference. Now, 6 months later, the Earth is tipped. We are now pointed in the northern hemisphere away from the sun. That same kind of patch of sunlight, look how much of the Earth it's covering at this point. Let's compare those two areas for size. It's like twice as big, right? So this is just a crude sketch, but it gives you some idea. The same amount of thermal energy from the sun is trying to heat an area well over twice as big. It's just not going to do as well. It would be like having a space heater in a small room, and you take the exact same space heater and put it in the middle of a gymnasium. Well, do you think it's going to be able to heat up that gymnasium very effectively? No, it's not. It's the same amount of heat coming out of your space heater, but the area it's trying to warm is just way larger. And that's what's happening with the tilting of the planet away from those rays. You're getting very indirect rays, not very efficient at heating. Now another cool thing that happens at the winter and summer solstice is where would the sun actually be in the sky? I've already told you during the summer months, the reason it's summer is because the sun is impacting Earth more directly. The sun is going to be much higher above you, right? So if at this point of the June solstice or summer solstice for us in the northern hemisphere, the sun is going to be directly overhead for people on the Tropic of Cancer, right, which is one of these latitude lines right here. For them, the sun will be directly overhead. For us in the north, it's not going to be directly overhead at noon, but it's still going to be pretty high in the sky. The sun will be up a long, long time, and it's going to be up very high. So the rays coming in can kind of impact directly on the Earth, very concentrated, very much able to make the Earth much, much warmer. Now we're coming up to the December solstice in just a couple days, and now the people at the Tropic of Capricorn in the southern hemisphere, the sun is directly overhead at noon for them. For those of us up in the northern hemisphere, just look at how you have to look down to see the sun. You're already looking way low on the horizon. to be able to see that. So instead of looking straight up to see the sun, you have to look down at the horizon because the Earth is curving away. You can see that. Look at this little smiley fellow that I have up here at the Arctic Circle. He actually doesn't even have a line between his eyes. Now I've drawn it exaggerated for scale. There's no line between his eyes and the sun at all. The sun is completely blocked for 24 straight hours. This is the cool thing about the Arctic Circle. In the December solstice, there are areas, all the areas above the Arctic Circle will be receiving no sunlight at all. Permanent darkness. Conversely, during the June solstice, again, you can see now, imagine the Earth is rotating about this polar axis. Everything above the Arctic Circle never has any nighttime at all. During this rotation, no matter where this guy's standing, here or here or here or here, even as the Earth rotates, everywhere he stands, you're going to be getting 24 hours of sun. So you get some really cool, interesting effects due to these summer and winter solstices when you live above the Arctic Circle. Let's go ahead and take a look at that. I'm sure most of you have never seen this. This is why we call, in the Northern Hemisphere, we call the polar regions above the Arctic Circle, we call it the land of the midnight sun, because even at midnight, the sun will still be shining. It will never set. 24 hours of sun a day. Let's go ahead and take a look what that comes from. This is a time-lapse shot. You'll be seeing the time right down here. I'll be reading out the times for you. This is starting at 2031, which is 8:30 in the evening. Let's see what happens. 8:45, 9 o'clock, 9:30, 10 o'clock, 10:30, 11 o'clock, 11:30, there's midnight, 12:30, 1 a.m., 1:30, 2 a.m., 2:30, 3 a.m., 3:30, 4 a.m., 4:30, 5 a.m., 5:30, 6 a.m. All right, the sun never went down. Even at midnight, the sun was still above the horizon. This is what we mean by the land of the midnight sun. 24 hours of sun due to the fact that the Earth is tipped towards the sun. And even as it's rotating, you never go into a place where the sun is not illuminating you. That'd be a pretty cool place to live. But conversely, you might get 24 hours of sun at the summer solstice, but in the winter solstice, you're going to pay for it by getting 24 hours of darkness. Now, this is Fairbanks, Alaska at the winter solstice, not quite above the Arctic Circle. So they are going to get a little bit of sunrise, but not very much at all. Let's go ahead and take a look at what happens on the winter solstice up in Fairbanks, Alaska. So this is sunrise, quote unquote, during the winter solstice up in Alaska. Here comes the sun. 10:54 a.m. comes your sunrise, right? It looks like early morning, but it's almost noon right now. 10:54 a.m. Look how low in the sky the sun is. It's never going to come up much above the horizon. You can see how it's not going to be warm. Do you see how low the sun is? Those sun's rays are coming at an angle, not efficient at warming you or the planet at all. There's noon. Look at how low the sun is at noon. Right? There's just no way that those rays hitting at a glancing angle are able to warm anything. That's what's leading to winter. All right. So they get 3 hours and 40 minutes of daylight at the solstice in Fairbanks, Alaska. And here you're seeing it. It looks like perpetual sunset, actually. Now the sun's going down at 2:40 p.m. That is a very short day. 3 hours and 40 minutes of daylight up in Alaska. This would be at the solstice around December 22nd. That happens every single year. So thank you very much for that very interesting time lapse of the winter solstice in Alaska. That'd be a pretty hard place to live when they have that much darkness. There's another way that I can show this to you and prove that the sun is actually sometimes very low in the sky during the winter solstice and sometimes very high in the sky during the summer solstice. So this is something called a solar graph. This is really, really cool. And I'm going to show you in a second how to make a solar graph. So this might be something that you all want to try to do. It's a really cool science experiment, not very hard to do, and there's no moving parts at all. So thank you to this, to Ian Hens in Medicine Hat, Alberta, created this solar graph between the June solstice and the December solstice. It shows the path of the sun, and there's this really cool teepee in the picture as well. This is a time lapse, kind of integrated picture that shows where the sun was on every given day. You can see that on the winter solstice, December 21st, 22nd, this was the lowest point in the sky it was. So this line right here would have been the path of the sun across the sky on that date, December 21st. And then every day after the 21st, the sun is slightly higher in the sky. And so you can see that's why the days get longer. It just takes longer for that traverse to actually happen. It's just a longer path. So of course the day is longer. It takes longer for it to come up and trace this path out. And now here is the summer solstice on June 21st. It's the highest point in the sky that the sun will be. And we're missing the top of the picture here, so we can't see quite how high up in the sky it is, but it'll be pretty high up in the sky. And that's the summer solstice. It occurs around June 21st. And after the summer solstice occurs, then the whole pattern repeats itself and the sun will start to be lower and lower in the sky every day. And then fall will come and then winter will come as the sun is getting lower and receiving less of that solar radiation. That's what the seasons are. That's what causes it. So a solar graph is a really, really cool thing. So I'm just sharing the screen for you from this nightwise.org. You can go on the internet and see how to make these things. It's just a really cool idea. It's basically just, it's a way of making a long duration image of the sun's path by a simple pinhole camera, right? So a pinhole camera is essentially, in this case, they're just using an aluminum can. You can see here's just an aluminum can. You do need to get some black and white photographic paper, which is what this paper is right here. And then you need to seal it up really well. And then you affix it somewhere where it can see the sun. And here, looking down into the pinhole camera, it's really cool. You can actually see this white dot here. That's the little pinhole in the wall of the can. It looks like they painted it black inside the can. And then here, this little white spot, that's, you can actually see the image of the sun. So the sun must be up here somewhere, shining through that pinhole and making a little dot here. And because that's photographic film inside, and you mount this very rigidly somewhere, you take some wire, strap it down, or duct tape somewhere where it's never going to move. You don't have to do anything with it. You just leave it for 6 months. And then every day as the sun crosses the sky in front of you, that little white, bright bit of sun is going to traverse its way across your photographic film, and it's going to make some pattern that looks like this. So the cool thing is not only do you get the patterns of the sun every day, and that's what these bright white lines are, but whatever you're taking a picture of, in this case, this is Union Station in South Bend, Indiana, right? You can see the cameras looking at the station. You can actually, you do get a very faint, latent image of the thing in the background as well. So you don't just get the sun. So that's pretty cool. So that's called a solar graph. Not very hard to do. I think if you guys want to try a cool little science experiment, you have a neat place in your yard where you can mount this up permanently and it won't be disturbing anybody and it won't move or blow away. You might want to try making a solar graph. That's pretty cool. And then one last thing you could do is if you could take a picture of the sun in the sky every day at exactly the same time, that would be the key. So say you had the ability to go out every day at noon and stand in the exact same spot and take a picture of the same patch of sky exactly the same every day. If you could do that and then overlay all these pictures together, then you will actually see the motion of the sun through the sky. You will see at noon, for example, every single day, the sun's in a slightly different place. All right, so it's kind of, sometimes it's lower and sometimes it's higher. And obviously what we've just seen is that the winter solstice is that date when the sun is the lowest in the sky it's ever going to be. The summer solstice is that point when it's the highest in the sky that it's going to be. And then it kind of curves out this really cool figure 8 shape called an analemma. And that's really, really neat. So it's like a pinched figure 8, and that's there's a bunch of cool reasons why that is, but you know, that has to do with the motion of the earth around the sun. But that's a really stunningly visually striking way of actually telling how we are moving around the sun, that you can actually just see this motion right there. So that's it. Yes, in fact, the Starks were correct. Winter is coming. There's no doubt it will be here on December 21st, according to our solstice, right? So for us, the December solstice is our winter solstice in the Northern Hemisphere. It's coming, shortest day of the year. Temperatures are going to get cold, nights are going to get long, and that is what winter is all about. But fear not, my friends, summer will be here again on June 20th, June 21st, just like it is every year. One thing we know for sure about the winter solstice, 6 months later, we'll be back at the summer solstice. So here's actually showing in the Northern Hemisphere when we have summer, when we have winter, when we have the autumn and vernal equinox. One thing that is really important to mention, and I should just myth bust this for you really quick, take a look at the distance from the sun that the Earth is. Here's the winter solstice. We're the most tipped away from the sun, but during our winter solstice at the Northern Hemisphere, that is actually the point in our orbit when we are closest to the sun. A lot of people mistakenly think that winter happens because we're the furthest away from the sun. That's actually not true. Winter in the Northern Hemisphere is actually at the point in orbit when we are closest to the sun. So that argument does not work at all. It has everything to do with the tipping of the planet away from the sun and really nothing at all to do with the distance from the sun. And you can see it doesn't change all that much. These are astronomical units, the units of the sun, but during our summer solstice, that's actually the point in the north when we are furthest away from the sun. So really important that you have in your mind the idea that no, it doesn't have to do with your distance from the sun at all. It has everything to do with that tipping of the axis away from the sun. And now you know exactly what causes winter. Now you know that winter is in fact coming, but you're not going to worry anymore because you know that summer will be here in a very short 6 months. So thank you so much for joining me, everybody. I appreciate the time you spent with me. I hope you learned a little bit about winter, and we'll see you again in the new year. Have a great holiday, and I'll see you in 2022.